Hello everybody. The main objective of this second part of our historical overview on Thomas is very simple. We want to see how the Thomas or Thomas Fermi formula is linked to density functional theory. In the previous video, we have seen that in order to derive this simple formula for the potential felt by electrons inside an atom, the density had to be put at the very center of the theory. It is the crucial quantity of the method. What about the connection with density functional then? This is the scope of this video. So let's start by writing the total energy in the Thomas Fermi approximation following the density functional approach. Let's see where this takes us, okay? The total energy functional will have some kinetic term to be statistically evaluated following Thomas's approach, an energy term due to the electron-electron interaction, sometimes called internal energy, as opposed to the electron-nuclei interaction, which is related to an external potential, for example, the one of the nuclei, with their fixed position in space. Actually, an important role, at least quantitatively, is played by the nuclei-nuclei interaction, but this is only an additive term. It doesn't depend on the electron density. We do not care about this term at the moment. So let's build this functional, following Thomas. If we start from the last term, we immediately write the energy functional in terms of the external potential. Typically, as I said, this is simply the potential of the nuclei fixed in position r here. This part of the functional doesn't present any issue, and it is the same that appears in density functional theory. Let's go on to the other interaction term, the electron-electron interaction. Here, we follow a completely classical approach, in which each electron, which occupies a position in space r according to electron density n, interact with the electron density created by all electrons, via the Coulomb interaction. This is true for any couple of electrons in all space, so we integrate over space, and of course, we pay attention not to count the same couple of electrons twice. You might recognize the classical electrostatic term here, also known as the Hartree term. Finally, let's write the kinetic energy, which is a simple functional of a power of the density. It is not difficult to derive this formula, starting from the semi-classical approach of Thomas. However, this is also one of the exercises of the module, so don't miss the lecture notes, where you will find all the details to do the exercises, and in particular, to understand why the kinetic energy can be written like this. What it is sure is that now we have a full energy functional of the density. Let's have a look over here. This is the expression of the total energy in the Thomas or Thomas Fermi approximation, written as a density functional. And the question is, how to recover the old Thomas formula? How to connect the two? This connection was established in 1932 by Lenz and his student Jensen, using the variational principle. In essence, what we ask is the best density for the functional above. The variational principle says that the best density is the one that minimizes the total energy. So what we have to do is a minimization procedure. We search for the density that minimizes the energy functional. And among all values, we search only among the densities that are normalized, that give the correct number of particles. It's a constrained minimization procedure, for which we use the Lagrange multipliers method. We minimize the total energy by variation of the density, but keeping the number of particles, of electrons in our case, fixed and equal to n. Let's start then. We write our total energy functional of the density, where again we recognize the kinetic term, the Hartree term, or the electron-electron interaction term, and the external potential, in our case, the electron-nuclei interaction. So we differentiate, which is essentially a functional derivative with respect to electron density n, and we obtain this formula. So all this has to be 0. And since this has to be 0 for a generic density variation, the integrand here has to be 0, which leads us to the final result, the Thomas Fermi equation, though here it is given in the integral form. Now, if we call the total interaction V, we arrive at the differential form of the Thomas Fermi equation that we read in the original Thomas's paper. Again, the actual derivation from here to here is left as an exercise. It's just a little math problem. You will find more details in the lecture notes. We have seen then how the original work of Thomas was strongly connected to the concept of density functional. Not only the density of electrons was a crucial quantity of this approach, instead of the many-body wave function, but as we have seen here, following the demonstration of Lenz in 1932, the whole approach can be seen as a fully density functional approach, 40 years before the Hohenberg-Eckert theorem. The Thomas Fermi method has been extensively applied before and after the birth of density functional theory. It's not the scope of this module to talk about the many achievements and application of the Thomas Fermi equation. If you are interested, you will find more info in the lecture notes. However, thanks to this connection, we are also able to see what are the limits of the Thomas Fermi approach. And this is the aim of the next video. Don't miss it. In the meanwhile, I say goodbye.